Welcome to my presentation about TabNet. TabNet is an attentive interpretable tabular learning proposed by Arik and Pfister in 2019. I'm Marcel One, and this work is for the Spring 2024 Deep Learning with TensorFlow, or in this case with PyTorch. So let's start by covering what's TabNet. TabNet is a novel deep learning technique that was developed by aiming at developing new solutions for tabular data. This alternative would offer a deep learning approach for a field that's mostly dominated by ensemble decision trees. Among its many options, this new model offers the capabilities of dealing with multiple data types, not needing feature engineering, and allowing for performance and efficiency. It's also able to use representation learning to learn from the different features and their relationships, and can perform tasks of classification and regression. Its main advantages are that the tabular data can be inputted without any preprocessing and uses sequential attention to select the features. This is done in a single deep learning architecture, thus enhancing performance and efficiency. And these attention layers also allow for efficient learning and interpretability of the models. So let's quickly go over the structure behind the TabNet. And although it seems very simple, we'll break it up. It's a sequential multi-step processing, so you can change the number of steps that the model goes through. In each step, the processed information from the previous step is retrieved, and an attention layer decides which of the features to aggregate into the overall decision and to the next level. Because these outputs then are processed, and the feature representation is transferred to the next step. This is done through the use of an attentive transformer or attention layer, which uses a sequential interpretation to select the most useful features and their relationship, and to allow the further interpretation of the model. These these features are transformed using a feature transformer, which is also sequential, and transforms the attention selected features into more useful features on each of the steps. The attention transformer starts with some fully connected layers, following by batch normalization and sparse max normalization. This sparse max normalization is used to generate or to establish a learnable feature mask. The soft selection of the salient features are selected using sparsity, which enhances the learning capacity of the model by establishing which of the features are more important, and thus optimizes the parameter efficiency. It also allows to keep track of the contribution of each of the features to the overall model and how that has changed over the steps. The feature transformer, on the other hand, uses the feature transformation to use the decision step dependent features, but also the global features that haven't been transformed. It's made up by fully connected layers, followed by batch normalization, and gated linear units as activation. Then there's a normalization to stabilize the learning and the variance through the network, because otherwise the authors found that it would be prone to explode. So following with the overall architecture, after each of the steps, the weighted coefficients of the used features are learned by ReLU activations and added up at the end to generate the aggregate feature importance mask that is then used for global interpretability. The parameter, because of its complexity, has many hyperparameters, such as the width of the decision prediction layer. Uh, the name is self-explanatory. The attention embedding layer and its size. The number of steps, so how many times we go through this feature selection, attention, and transformation layers. And the gamma coefficient, which can regularize how much some features can be repeated across steps. So if we establish that some feature can't be used many times, it will be learned on the first step, but never be used on the following ones. And then the number of independent or shared activations that you can use on in each of the steps. The lambda, the lambda sparse, it's a regularization parameter as well that uses to that is used to select the most appropriate features. The model, the authors tested the model on various benchmark datasets, such as the forest cover type dataset, that is a classification task, and they vet other state-of-the-art models. The poker hunt induction dataset, and this is mostly interesting because not only did it beat the previous results, but it also obliterated it. This is mostly because the model is, as I said, is able to learn feature and associations between the features. So in this context, this problem would make a lot of sense because the quality or the poker hand you have depends a lot on the relationships of the cards that you have and not just on the numeric or the sign of the card. And lastly, they also show that solving a multi-regression, I say multi-regression because it's the task on the Sarcos dataset is using, if I recall well, 21 variables or features to predict other seven. So that's what I mean by multi-regression. And it has some tools for the other most important advantage of TabNet is the interpretability. It allows to visualize the aggregate feature importance mask, or also regarded as global interpretability, and it gives the overall contribution of each of the features in each of the steps and aggregated all together using the learned weights. And it can also serve to plot the decision step masks. So much of the or which features is the model learning at each one of the steps. This is useful because usually the first steps are the ones that are most explanatory, and as the model increases in complexity, it finds more subtle relationships. So this model has been used both in different benchmarks, but we'll focus on the PyTorch implementation, but most being more specific, the FastAI because of its ease and although these have been implemented outside of the original paper, they follow the guidelines and the instructions given by them. So I'll show you an example of how I use this. As I said, I focus on the FastAI. So I'll use it on a specific problem where we are dealing with a multi-class classification task between three classes, and we have a dataset that is roughly 4,500 images from the Brax dataset. And these images have been processed, and we've extracted 25 biologically relevant features from the images. So we have a tabular data that's 4,500 by 25, um, 25 features. The train test split has been done by the dataset. It's already decided in the dataset release, so I'll show you the GitHub code, the Jupyter notebook on my repository. So here I explain a little bit I had covered in the what I have covered in the slides, but it's really easy to use as a baseline. What is a little bit harder is to optimize the hyperparameters because it has many settings, so we'll cover those now. Here's the extracted features from the images. I load them, and here I create the data loaders and the tabular pandas, whatever. This is regular fast AI. And this is where we start dealing with the parameters for the models. We generate the embedding size because the model also learns from not only continuous variables but categorical variables. In our case, none of them is categorical, so this will be empty, as you can see. And here we are creating the models. First, we start with a really big model uh, many with the size of the attention and the decision layers being really big, but with only two steps. And we do the learning rate finder that is usual in the fast AI framework, and we fit for 200 epochs. Let me scroll through this, and we can see that the model is very slow in learning, although we can see a big drop in variation at first, then it kind of lays flat. So as an altern, well, you can see that the lowest variation loss that we could get was 1.09. So we tried increasing the model size and the complexity. The authors of the paper recommended to keep this low and usually similar between them. But if we wanted to increase the number of steps, we could use this to multiplicatively increase the size. So once again, we train this time for 100 epochs, and we can see that the valuation and training losses are getting lower, much faster, and we achieve the lowest valuation loss at around 47 epochs, and it's 0.69. We then test that this model is performing well by looking at the precision, recall, F1 score, and accuracy of the model on the test dataset, and we reach a 65% accuracy, and this is the correlation matrix. And well, as a benchmark, we can say that the model is learning something because a model that would randomly predict the predominant class would only get a 42% accuracy. And then the most interesting part is that we can use the interpretability to understand how the model is learning the different relationships between the features. And here, if I zoom here, you can see here the sample number in the test set and the different features, and you can see that there are some ones that are given a lot of attention consistently across samples. For example, the texture, the perimeter, and the area, or the smoothness, the standard deviation of the smoothness, the density, or the area. And here you can see the global interpretation or contribution to the model. So, for example, if in this context, one of the applications for the interpretability would be radi- not radiologist, but the expert in histology images utilizing this model on or one trained on even more data and make a prediction, and they would have the image on one side and see which features the model was using to make that prediction and try to understand it in a way. So perhaps that would make it easier. Here I do an example on one of the test images in that very same context. And here we can see that the various predictors are the density, the limit or the maximum area values for the nuclei, the standard deviation of the smoothness, and the mean of these features. And this has been all. I hope you found this useful and that you learned something about it.